Good morning. It's my great pleasure this morning to introduce Professor Mladen Kezunovic. Mladen is the Eugene E. Webb Professor at Texas A&M University in College Station, Texas. Mladen comes to us not only with a very large academic experience, but also has worked in industry for Westinghouse Electric and Energo Invest in Europe. Currently, he's also the director of the Smart Grid Center and a deputy director of an NSF IUCRC Electrical Vehicles Transportation and Electricity Convergence at Texas A&M. He's also the president and chief executive officer of Expert Power Associates, which is his own consulting company. Mladen has also published no less than 450 journal and conference papers. He's a fellow of the IEEE, an IEEE Distinguished Lecturer, and a member of SIGRE. And last but not least, he's also a professional registered engineer in the state of Texas. Mladen, thank you very much for coming today and talking to us.
Thank you, Daniel. It's a pleasure to be here. As a matter of fact, the last time I've been here, it's been a while. It's been a few years when some of my good friends actually graduated out of here. But you don't want to know how many years back that was, a long time ago. So anyway, we're going to talk about the data in power systems, and for whatever the time allows us here to explore, we'll talk about different aspects of data and different uses of data. That's what we're going to do. I'm coming, as Daniel mentioned, from Texas A&M. We have a center there, and I'm just introducing a few projects that are underway at the center, just as a background. Now, what I tend to do in these presentations is I tend to tell the entire story briefly at the beginning so that you can go home right after that if you have to. And if you're more interested, you can stay and hear further details. So I'm going to tell you actually the story. I have been intrigued, like many others over the years, what can we do in power systems if we have more data, different data, integrated data? So it's the relationship between the power system applications and data. So the focus is on data. You can formulate the problem almost any way you want, but one way is to say, what can I do differently if I have access to more and different data? So that's the focus of this presentation. That has been a focus of my research for years. I may have not been able to articulate this each time I write a paper or give a presentation to a full extent, but if you are interested in reading some of these things that we wrote, they will always come to the same issue and the same problem. And they will discuss different aspects of it. Now, in order to see how I can use the data and understand it better, I have to understand the properties of data. So there will be some discussion about the properties of data. The other part is what we call translational knowledge, but it's really how do you use the data to actually develop applications for power systems? It turns out that one approach that is relatively simple to understand, maybe not as easy to implement, is to actually use the models of the power system, which can be improved by improved data. So using improved models, and use the data and match the data with the models to actually tell what's happening in the system. Because if you have a good model and you are simulating the event and you can corroborate that the event has occurred with the data, then the model tells you what actually is happening. It's a very simple concept, and it works. It works in many applications. It doesn't work for everything and anything you want to do, but it works in many applications. So that's the translational knowledge part of this. However, there are issues about implementation of all of these things with data, because a lot of us assume, for various reasons, that the data is good as it is. And actually, in many instances in power systems, the data, as it's being measured and communicated and whatnot, has a pretty actually bad properties in terms of quality of service, if you will, associated with the data. So even though you may be dealing with a very accurate system as it is designed, by the time you get the data to your applications, you actually are getting pretty distorted data. So the big issue is, as you use the data, how do you develop methods for actually verifying the data, understanding sensitivities of applications to the bad data and various problems in accuracy and, as I said, quality of service if it's being communicated, for example. So I want to bring to your attention some of the issues in that area under this title of implementation. So that's the package for today, if I may call it that way. A little bit of a property of data, a little bit of applications, and a little bit of implementation issues. So that's what I'm going to cover today. Now, to give you a background that all of you know, but there is a reason for repeating a little bit of this background, and that's associated with the smart grid and the semantics and legislative actions and integrative view and technology landscape, as I will be elaborating. First of all, let's talk about the smart grid. Please look at the terms that have occurred with the sources, organizations that have introduced the term. You can see IntelliGrid, WiseGrid, FutureGrid, Modern Grid, Empowered Grid, Perfect Grid, and the smart grid. Now, I am not here to discuss the terms, of course, nor am I here to express my excitement about the smart grid term or anything like that, but I am here to tell you that the smart grid is an official term that is actually contained in the ESA Act of 2007, Energy Independence and Security Act of 2007. Article 13 is titled Smart Grid. So our legislators have adopted the term for good or bad, and they are using it to actually designate many, many new developments in the power system. And the reason I'm bringing this up is that a lot of these developments actually are based on the fact that there is additional sensing infrastructure, communication infrastructure, technology, processing infrastructure that is based on a huge amount of data that is being generated with all of these devices and systems. So the whole development of the smart grid has created an explosion of data. If you want to look at that aspect only, there's an explosion of data. So now, what is the issue if I have an explosion of data? The issue is this: I have a technology, whatever that might be, whether it's a smart grid, whether it's a phasor measurement units, whether it's whatever it is, and that technology creates data. And then I want to use the data for an application. However, I need to close the loop to a business case. I need to create a sustainable business case for the use of technology. In this case, in my case of a discussion, use of data for doing something different or better in a power system. So this brings you to one interesting concept here. The data has a value that is monetary value, basically, at the end of the day. So if something has a monetary value, then of course the quality of that is very important, because that dictates whether that monetary value can be actually returned, because it's typically invested first to get the data before you can get it to use that for a return. So you can see now a relationship in this business model where you're investing in data and you're asking yourself, the applications that are going to be based on this data, are they going to pay back that investment? One of the problems that we looked at down at A&M was, if I want to improve outage management in distribution systems, and typically if you study that area, you can do a better fault location and a better restoration if you have more measurements. So therefore, the question is, how much should I invest in additional measurements to get improvements in the outage time or reduction of the outage time? Because the reduction of the outage time has a monetary value. Therefore, I can judge whether I should invest so much, whatever that is, to get that gain. So there's an optimization process going on between the additional data requirement and the return through the reduction of outage time. So that gives you a little flavor of this business component of this. Now, all of this has brought a lot of technologies, and I can list here as many as 100 slides of technologies. I just picked up some for the sake of the ones that are in the power electronics area. I put some power electronics as enabling technology, energy storage. I think Daniel works on that. But a lot of technologies are in the data communication, sensing, visualization, processing, storing. A lot of stuff is going into that area. A lot of stuff. If I look at the projections of the technologies, this is a typical curve that is used by consulting firms like Gartner, where they're tracking technologies. By the way, this is 2008, and it's intentionally taken from that year, so that you get a feel where some of these technologies have moved. The curve, incidentally, talks about the hype. You have a new technology, and then the technology reaches certain max in terms of people getting excited, then people start realizing certain issues with it, and it may or may not survive. If it does survive in the second belly, it becomes an established technology. So if you look at the technologies that were tracked, you will find quite a few that are actually related to measurements and data. If you look at the, okay, so I'm going to speed up a little bit through this because this may be, if you look at the projections for 2013 in the IT technologies, just IT technologies, by Gartner, this happened to be by Gartner, you will find all of these things that you can recognize, but the challenge I'm putting in front of you is, can any one of these things be used in a power systems? And I'll tell you the answer that I have, every one can be, and has a great potential in the power systems, every single one. And so that's where we are with this technology. Technology is penetrating, technology is offering possibilities. Technology is going to give us additional data. Additional data is going to give us a chance to develop new applications. But can we close that business loop that I was referring to earlier, investment versus return? That's where the rubber hits the road. And if you think about this, if you analyzing this, studying this, whatever, keep that in mind, if you will. It will be helpful. Now, let me go to the properties. And I'm going to go relatively quickly through some of this because it's pretty obvious. I'm going to spend a little time on some things that are more interesting. But in general, we have the power system in the middle with all of these domains. I just enhance these domains on the sides. I have customers and service providers and markets and bulk generation. If you look at the transmission and distribution in the middle, that's our core area in the utility business plus the generation. There is plenty of communications going on. There's plenty of data being exchanged. There's more that can be measured and exchanged. But if you look at the customer, if you look at the services, if you look at the markets, there could be much more loops closed, or many more loops closed on new data, new ways how the data is processed and in what time frame and things like that. So those are the areas that could be expanded, particularly the customer side, significantly with the use of data and applications and things like that. Now, I'm trying to zero in a little bit to correlate the events in the power system to the far right-hand side to the models that are used. The notorious thing in power systems, as you may know, is that we don't have one model that we can use to represent the dynamics of the system. We have to break it into different types of models, phasor-based models, time domain models, and so on. These models are on the right-hand side. Those are typically purchased as packages for short-circuit analysis, stability analysis, time domain analysis, and so on. So when I have an event in the power system on the left-hand side, I actually can create a model and simulate that particular event. That's the point. That's how we analyze the systems. That's how we operate the systems. We actually model and simulate. And based on that, comparing to certain measurements, we are making decisions how to operate the system. In the middle was just the actions that actually cause the changes in the power system dynamics. So this gives a correlation between the event and the model. Well, obviously, the event, if I have something to measure and track, I can directly correlate data to the models because the data represent the event. So now I'm in the business of comparing data to models eventually. Now, I can expand this concept of a physical system and physical measurements to a concept of the states in the market as well. So in the electricity market, I can also have the states that correspond to the normal emergency restorative states in the power system. And those are by either the configuration of the participants or the market parameters. So I can tie through data both physical systems and markets. And actually, the data becomes a glue between the two. So I can develop something that is an alarm processor in the physical system and attach all of these economic consequences and call it an economic alarm processor that actually gives a mix of identifying the events in the power system that have a direct impact on the market conditions in one solution. And so I'm gluing the data from physical system, market system, through this modeling of this alarm processor and getting answers to certain questions that I can pose both at the physical and market level. Now, the other thing with data is that data comes in time. The dynamic system changes, and you take a snapshot now and take a snapshot later on and so on. It's going to be a different dynamics because power systems change all the time. As a matter of fact, the power systems are never in a true steady state, never. There's always something happening in the power system. Now, how abrupt that is, that's a different question, but something is going on all the time. The other thing that is interesting with the power systems is that there are events that are local events, and these local events may have a consequence of the entire system or may not have a consequence on the entire system. They may be contained locally where they occurred. So now, therefore, I have the concept of time associated with data, with measurements, and I have a concept of spatial displacement, where these things are. And are they correlated, or are they just local? So two properties that are relatively simple, time and space, are very important in understanding how the data may be used for applications. Very important for understanding. So I'm going to try to shed some light on these things. This chart shows at the upper level the sampling rates that are used to collect data with different types of devices. Incidentally, I'm going to use some jargons here. You are probably familiar with them. But most of these measurement devices for transmission distribution system are located, most of them, not all of them, are located in substations. So we call them, they are all computer-based lately, so we call them intelligent electronic devices. That's a term that is used to cover remote terminal units of supervisory control and data acquisition system, protective relays, recorders, controllers, on and on and on. So those are IEDs. The IEDs sample the analog quantities and convert them into a computer word. So I have a sample and hold, a circuit that is allowing me to sample, and I have A to D conversion. The circuit or the chip that allows me to convert from that value that I sampled to a word, computer word. So I am dealing with sampling in order to get data. You can see the range of sampling. I can go at seconds, at fractions of a second, at milliseconds, at microseconds, and all of that, depending which ID I'm using. I will be talking later on in a minute about the problem of merging data. Because one issue is to get the data, the other issue is to integrate the data. There's a value in integration of data. Well, first you need to know what these sampling properties are. You cannot merge apples and oranges. But the signal processing theory allows us to merge data with different sampling rates. Because we can, I can't pronounce, interpolate, get more data or less data out of samples that I'm taking, and therefore I can match the other sampling rates. The other thing that is very important is we're dealing with a three-phase system. In a three-phase system, I have 3 voltages, 3 currents, whatever it is, and the relationship between these phases, the quantities in the phases, is very important for some of the applications. So we have a concept of synchronized sampling versus scanning. Synchronized sampling is if I am sampling on all of the phases simultaneously, and the scanning is if I go from one to another and sample after a time delay. The solution to this is using a single sample and hold that is, well, actually using the sample and holds on each 3 phases, but single A to D converter with multiplexer. So the multiplexer goes to one sample and hold, to another, and I have a time skew. So when I convert them, they are skewed in time. That's scanning. If I am sampling them simultaneously, they all may have A to D converters, and they all are lined up. That also needs to be understood. RTUs, remote terminal units, in SCADA systems, supervisory control and data acquisition systems, are typically scanning, while the data in relays and recorders are typically synchronously sampling. So if you want to merge data, as I will be talking about later on, you need to also understand that. The other thing is, we all know this, but we tend to forget. What is present now will be past tomorrow. What is future now will be present tomorrow. What I mean by that is that the concept of historical data, real-time data, planning data, actually shifts with time, which means that from the historical data, I can actually project back into the uses for real time and for planning, as long as my history is not abruptly changing. So this is very important to remember. So there are concepts that are introduced that I'll just throw them in. There are corrective actions, predictive actions, and things like that. They are actually based on what type of data you use to do what. You may use historical data to do actually operational planning. And you may make corrections as the data moves from real time to history on the fly. So those are the kinds of things to also observe. In terms of the conversion, I don't think I want to spend too much time on this. I can tell you one thing, that in the A to D conversion, if those of you that studied that a little bit, we have what is called a vertical and horizontal resolution. The horizontal resolution is the sampling rate. The increased sampling rate does not provide more accurate conversion. It provides a better view of the waveform, but the accuracy is associated with the bits, with a vertical resolution. And so I hear this, frequently, this device, samples really high, therefore it's more accurate than the other one, and unless you look at the A to D converter resolution, you don't really get the sense of what the accuracy is. Again, that's the issue that I was referring to. This is just an elaborate discussion, a little bit more elaborate discussion of the sampling versus scanning, but there is something here that is new in this slide that I haven't mentioned before, and that's the time stamping. So besides sampling data, I also want to know in the power systems when this was sampled, particularly in time, in absolute time, and in relative time. So I want to know when this sample was taken against that sample in relative time, and I also want to know when these samples are taken in the absolute time. So one way of doing this is using GPS receivers. Now, all of you are familiar with GPS. You're using it for navigation. They also have, the system of satellites has a very accurate time reference that is coming down. So you can use the time reference, and that is used through what is called 1 PPS, coming out, pulse per second, coming out of the GPS clock, going directly into the sample and hold of a device which assures that the sampling is taken at the same time. Now, you have to sort of think about this. If a device is put on one transmission line, like relay, protective relay, then the signals are sampled across 3 phases. But they may not be synchronously sampled in comparison to another relay on another line in that substation. While if you are dealing with the digital fault recorders, that are typically recording waveforms per substation, they are all synchronized across all of the channels in that substation. So that needs to be recognized. The other thing is the time code, the actual absolute time that comes out of these receivers that may be used for time stamping. That means I can put a stamp on a signal at the source, and I can correlate that to absolute time. This is very important when we are merging data from multiple IDs. For example, in synchrophaser systems, when we move data from a number of synchrophaser units across the system into the data concentrator, it's very important to know which sample comes when, to know whether they are all coming at the time when they should be arriving. Here's something else to discuss. A concept of a phaser. We have talked about samples from a waveform. So waveform can be anything. As long as you meet the sampling theorem, you can take samples. But we are used to the term phasers quite a bit in the power systems. Now, if you recall your definition of a phaser, constant magnitude, constant angle displacement to the reference, and constant frequency of the change of that signal. It's never met in the power systems, never. So what are we measuring when we are measuring phasers? We're measuring phasers in relays. If you know how a distance relay or impedance relay works, it is estimating a phaser. If you look at the phasor measurement units, it is estimating a phaser. But what phaser? Because the signals are, in many instances, in relaying in particular, abruptly changing, have all kinds of components. So for those of you out there that are really interested in phasers and measurements, take a home assignment to study the definition of a phaser under various transient and dynamic conditions in a power system, and see what you're going to come up with. It's a very interesting problem, very simple problem to define, maybe very difficult to actually deal with. So that's the concept that we need to deal with, because a lot of our modeling and simulation is in a phaser domain. So if you were to match the data to the phasers from simulation, you better have the right things to match. Otherwise, the match is not going to work, right? Okay, so by carefully selecting the data and deciding how you're going to use the data and merge and this and that, you can then develop different applications. So that's where we are with the applications. The spatial issue, this was all a discussion of the temporal issue and dynamics and all that. Now we are at the spatial issue. The spatial issue, what is interesting is that sometimes to solve a local problem, you may have to use a system-wide model. And vice versa. To solve a system-wide problem, you may actually have to focus on the local event. This is sort of interesting to observe. I'll give you a quick example so that you don't wonder. If I have a fault in a system, and I don't have the measurements at every end of a transmission line, but I have what we call sparse measurements. I have a measurement here, and a measurement there, and a measurement there. By the way, this is a very real problem. If you look at the tapped lines, you don't have measurements at taps quite often. Tapped lines are used in some major cities in a utility layout. And to locate the fault with the method that uses measurements from two ends, you don't have measurements from all ends. So it becomes sparse by definition. If I take a short circuit program and I start with a fault somewhere in the region and run simulations, and then I change the location of the fault and run simulations, and then I change and I run simulation, but each time I am matching at the points where I have sparse measurements, the simulation results with the sparse measurements. By doing an optimization, global optimization, I can actually find the best fit between the simulated values and the measured values, which means that that fit was created by a fault selected somewhere in the program. That fault selected in the program is the fault in the system. If everything in this matching process is done correctly, if the model is right, if the data is right, if the measurements are right, if everything is right, it actually should give you a pretty good result. Unfortunately, short circuit programs are set once in a while. They don't track the topology, so you have to have a method where you go to the SCADA Pike historian and you get a cut of the topology and match over here and in the short circuit program and match the generation and match the load and match this and that before you get a little bit better model, and then you have to deal with the measurements and so on. It's feasible. It can be done. We have done it. Some good results were obtained, and that's an opportunity. And it comes from matching the data to models. Now comes an interesting issue, which is the issue of merging the data. So it's a simple substation layout. Here, the lowest level A and S's are analog and status signals. And these acronyms are power quality meters, PQM, DFR, digital fault recorders, DPR, digital protective relays, PMUs, phasor measurement units, other IEDs. I may be integrating this. The question is very simple. If I have certain applications, am I going to get a better result by merging data or just using the data from one infrastructure? Because those become infrastructures. The answer is the better results will be obtained by merging data. And the question is why? If you look at the substation layout and the measurements, how they are taken, every single point in a substation has at least two measurements taken by two different infrastructures. So just by the virtue of redundancy, you are gaining something. Just by the virtue of redundancy. Let alone the fact that some data, as I was discussing, is more precise due to the sampling rates, due to the accuracies and everything else, than the data from some other infrastructure. So for example, if I'm using SCADA, supervisory control and data acquisition, and I'm worried about the topology processor of the state estimator, or the front-end state estimator, if I use data from relays and recorders, I can actually verify exactly whether the topology is as it should be. You may know that the topology processor may actually fool the state estimator, and the state estimator may actually diverge. If you look at the blackout in 2003 over on the East Coast, what actually has happened is that the topology processor has failed, the state estimator has failed. They didn't know what's going on in the system. They didn't know that the line between two operating regions was out. When they talked on a phone, and there's a record of that, much like when the airplane goes down, there's a record of that. One operator says, I see an open line. The other one says, I see a closed line. And so this had to do with these kinds of data that they are using. I always get amused, and I don't mean to offend anyone, but I get amused when somebody is trying to figure out from one infrastructure whether something that is obvious from the other infrastructure is actually happening. So there's a research out there on PMU measurements, analysis, trying to figure out whether a breaker somewhere else has opened. That breaker is monitored by a different infrastructure that can tell you whether that breaker has opened or not if you merge the data. I mean, that's the end of the story. Now, you may say it's difficult to merge. I don't know that it's difficult to merge. As a matter of fact, I think it's easy to merge. I merged data from different sources for 20 years and didn't find it difficult. So merging data in power systems at various levels has a tremendous benefit. And it's not done. It's not done today at any significant level. So that's an opportunity to explore, to research, to develop, to implement, and to take advantage of it. This is a little bit of a exchange of data. Goes back to the transmission systems, communication systems rather, data transmission. And I can have the needs to share the data within a substation to improve the applications. Those of you that have any courses or any exposure to relaying, protective relaying, you may remember that the power transformer is protected by current differential and some other adjustments to that. What would happen if you had a voltage signal available? You can discover the energizing modes of that transformer very easily by looking at the voltage. Voltage is not available in the substation. It's readily available to be shared. Readily available. Then I can exchange between two substations and gain. I can solve, for example, the partial differential equation in time domain, turning it into an algebraic equation at the end of the day, and solve for fault location by exchanging measurements from two ends. And then I can exchange across the system for various applications. Communication options, you all know this. I don't need to talk about that. We are today in a very broad area. We can use fiber. We can use microwave and wireless and stuff like that. I think I made a point with this. The only thing that I want to bring to your attention is a very important point, and it's written down at the bottom. In the power systems, we have a terminology that we use that is operational data for SCADA data, supervisory control and data acquisition data. That means operators are using that data to run the system. Non-operational data from relays recorders is triggered data. That means when an event occurs, the device triggers. That data is not used for operating purposes. However, if processed in real time and passed on and integrated to the operational data, it can bring a value, and it can be done. So the term non-operational data is a conditional term. It's conditional on how you're handling the data. There's nothing inherent with that data that tells you that it's not operational. It's how you're handling it. So if I handle non-operational data in a real time and turn it into operational data, I don't have non-operational data. I have operational data, period. But I have better operational data, okay? The other thing is situational awareness. Again, I don't want to offend anyone, people out there, but sometimes we agree, sometimes we disagree. Situational awareness doesn't have any meaning in power systems. No meaning. Why? If it's intended for the operators, operators don't have a concept of I am aware. They have a concept, this has happened, my book says I should be doing this, and hence I execute. Now, the fact that they may look at the data, hey, they are looking at football games on TV sets in the operating rooms too. I mean, they are looking at a lot of stuff, at weather data, they're looking at a lot of stuff. Yes, it brings some level, if you want to call it awareness, but it really is not directly used to operate. Now, if I have data analytics to turn that kind of data into actionable data, we call it, it's not information anymore. Information is extraction of features. It's knowledge. It's how I get from information to the cause-effect analysis, which creates a knowledge for action. Then it becomes an operational data. So at the end of the day, all of this maybe operational data. But what I'm missing for that is means of converting non-operational data to operational and means of converting what is called situational awareness data to operational data. And that is broadly called today data analytics. So that's a big area of exploration. We have explored it, others have explored it, and it's quite interesting. Now comes, for those of you out there that are into big data, now comes the issue, okay, if I'm measuring out of the system, I get whatever I get here that I discussed, what else is there to look at? Market data. Obviously, market data comes at different time scales, it comes at different types of information and so on. So how do I relate the market data to the physical system data? Animals. You may say, why in the world you picked up animals now? What is this all about? First of all, this picture in the middle is taken, for those of you that may be from Spain, is taken at Iberdrola's system down south at the time when the migration of birds from over the Gibraltar, when they came from Maghreb, from Western Africa, into Spain. Every single tower has them. Every single tower. What these poor things are doing, causing short circuits. The poor bear down there, you can see what he has done. So, if you are tracking, which is on the right-hand side, the migration of animals, birds and other things, you actually can predict where they can do the damage onto the system. On the left-hand side, these green things that you see are actually protectors for rodents and other animals causing shorts. So you can develop a protection, or you can develop different predictive techniques for even protection. Okay? The other is, and I don't need to tell you about GIS and GPS and all that. They come from different systems and all that. But it's interesting, from aerial views to seismic. This is the seismic data to the right-hand side. If I start correlating all of that, as you may know, it wasn't Seattle, it was San Francisco. It was the West Coast when we had this earthquake a few years back, 10, 15 years. The power transformers all went out because the Buchholz protection, that is a pressure protection, operated because there was a stress on a transformer. There was no fault on a transformer. There was a stress on a transformer, created gases. Gas-operated protection. So knowing all of these types of things, I can start correlating data in space, certainly, and in time, because these systems have dynamics. And I can go on and on. The weather, and there are many systems for tracking weather. There's a lightning detection network, a national network. There's other types of weather data. Now, with weather data, you can dig in and find all kinds of problems. For example, if you are in the wind business and you're trying to estimate the changes in the wind, unfortunately, there is no system that is very accurate that will measure the wind at that height. You can measure it lower, you can measure it higher. So some of these data sets, even though they are huge, they may not contain the layer that you want. But then they are equipping now, as you may know, airplanes are taking off and landing, and they measure actually at different levels as they pass. So you get some data points from these things that are moving. So anyway, for those of you that like big data, take my story from the substations and enhance the story with all of these sets that I gave you now and didn't have a chance to talk much about them, and think about how you're going to correlate this in time and space. Very interesting problem. We're working on it. A lot of other people are working on it. Very interesting problem. Translational knowledge. This is applications. I am not going to go over this at great extent. My time is expiring. I want to spend a little time at the end on the implementation. I will just quickly go through these different slides just to give you a flavor. But you need to separate out the type of data when you're matching to the type of model. That's the bottom line. So if I use sample data, or if I use phasor data, you can see here in the applications that I'm discussing, optimal fault location, intelligent alarm processor, inherently adaptive detection and classification of events, they have their temporal, spatial, and model dimension. And you need to understand that dimension. This goes on to illustrate different types of models that are used to match different type of data. Alarm processors, this has been a story forever for EMS systems since they were invented in the 60s and implemented in the 70s. People worked on intelligent alarm processors. However, people spend a lot of time trying to figure out smart ways of dealing with the SCADA data to figure it out what's going on. When the extension is made to the relay data, recording data, some of these things get far easier to conclude. The cause-effect relationship is much easier to figure out if you have the data that records actual events. And it's not difficult at all to bring that data in. We did a study for ERCOT down in Texas, and we laid it out how it needs to be done. They never did anything with it, but nevertheless, it's pretty clear how it can be done. This is for those of you that like data only, without the models. You can actually develop data models. But remember, in the background of all of this, you may be still using models, because in some of the neural nets and things like that, you are actually training them, and in training them, you're using models. So the model is in the background of these things. What this is we're sampling certain features out of the waveforms, we classifying the clusters with neural nets and filling in with some fuzzy classifiers, the spaces in between, and we are able to create a space that is partitioned, so each measurement, when it falls into that space, if it's in the red area, it's a fault. If it's in the blue, it's outside the zone. If it's a yellow, it's inside the zone, and it's not a fault. So you could actually create classifiers based on data mining techniques and some other techniques that are primarily based on data. But remember, there will be some training or learning in many of these techniques, and you may be resorting to actually models to do that. So there's still a relationship between the model and the data. It's just in a different way. Big data is big. It's big in every respect. It's big in the companies, in services, in whatever you want. It's all over the place, except there may be some misunderstanding between the big data people at Google and Microsoft and us in the utility industry. But after a few drinks, I guess we can get to an agreement what we mean by big data. And after that, it becomes the problem that everyone is trying to solve with some very similar techniques. There are a lot of startups in this. I want to bring to your attention, if you haven't heard about that, because it's good for research people. If you haven't heard about Green Button Initiative, go and read about it. Just Google Green Button. Green Button is a government initiative that is taking off big times, that is actually voluntarily asking the vendors of smart meters to open the data to outside use. Now, there are certain privacy issues, there are certain other issues that are there, but nevertheless, there is a mechanism to open the data. It's designed after a blue button in medicine that I'm told, I'm not a medicine or whatever, a doctor or anything like that, I'm not in healthcare business, but they are able to share certain patient information and whatnot by pressing a virtual button, which is a piece of software that actually pulls the data and allows you to use it. So look at the green button. Now the next is implementation. I think I have a few minutes for implementation. I don't want to dwell on cyber-physical stuff. You all heard about that, and privacy, very important issues. I will touch upon those in one slide each, just so that I don't appear not recognizing the value of these issues. But I'm not here to to explore on them. But I want to explore a little bit on standardization and testing and certification. So as far as cybersecurity, it's a business that is growing. If you follow what the government is doing and requiring for the utility industry, you will recognize that it's a huge item. And it will be a huge item in the future. So if you want to do your PhD dissertation on cyber-physical security for power systems, I can assure you that hundreds of those can go out. There are so many problems out there to solve, and it's an interesting area. And there may be even some funding there. The privacy is a different issue, of course, and the privacy is a perception issue, too. If you look to the right-hand side, some people that know more about privacy would have a stronger opinion. Some that don't understand the privacy have less opinion. But one thing is, the moment the data starts floating, a lot of things can be figured out of data. You've probably seen it. Secretary Chu, former Secretary Chu, is he still a secretary or is he former now? He's gone. I remember the news. Yeah, the news was a few months back. He was giving this example over and over. The government hired a firm to analyze the household data, residential household data. They could tell everything from this data. This is electricity data, everything. Who was at home, what they were doing, how different it was from this and that, and I don't want to go even into the details that they were able to figure out. So the privacy is a big issue, huge, and has to be dealt very carefully with. Now the standards. I have developed attachment to standards for a long time. I've been active in the IEEE. I'm also serving now on something that is called Smart Grid Interoperability Panel, an organization that is mandated by the ESA Act and was put in place under NIST, National Institute of Standards and Technology's umbrella until recently, this year, when it actually was turned to the private sector. It is actually doing coordination of standards. It doesn't develop any standards, it coordinates standards. Now, let's talk about these different three pictures out there. What do they mean? They are actually associated with how you deploy a system, whatever that system might be, SCADA system, metering system, any system. The one that to the left is what we call linear. You procure the system, you install the system, and you decommission the system at the end. That's the end of it. It has a life cycle, and it's gone. The other one is circular, over to the right-hand side, is where you procure the system, deploy, and then you take another version of it in the next cycle. This is typical for EMS systems, energy management systems. What happens is, after 30, 40 years, or whatever the cycle is, they would take a new one, and they would slightly modify the requirements and get some improvements, but it's more or less the same functionality. The one down below, which is spiral, is the most interesting one. It's the one where you continuously upgrading the system. Continuously. So the life cycle is never ending. So what is the example of that? Synchrophaser systems. The systems that are heterogeneous, that are built out of components that are not provided by a single vendor, but by multiple vendors. If you go into synchrophaser systems, the clocks are provided by certain vendors, PMUs by certain vendors, PDCs by certain vendors, and applications by certain vendors, and so on and so forth. It is most likely that in these systems, you will discover that one piece of something doesn't quite do what you want, and you want to replace it. And then another one, and another one, and another one, and another one. The problem is, it is heterogeneous, and yet you have one system solution. So what do? You insist on something that is called interoperability. And the definition of interoperability is simple. It is, if I have a device A and a device B, and I take the device A out and put the device C of the same functionality, it should be able to talk to device B. Now, how do I assure interoperability? Well, there is a necessary condition and a sufficient condition. Necessary condition is that the interface is defined by a standard. So we all comply with that standard. However, the standards do not cover everything. So the sufficient condition is that you actually exercise some sort of a test that shows that on all other fronts, these devices or systems would talk. That interoperability requirement is spelled out by an organization called Gridwise Architecture Council that has developed what is called WAC stack. WAC is the abbreviation for the organization. Stack is this interoperability requirement stack that starts from the basic connectivity and network interoperability, and syntactic interoperability, which is at a technical level, moves to the semantics, and then moves to the organizational interoperability. I will just point out two interesting concepts here. One is cybersecurity interoperability. I have designed a system that is cyber secure, but I'm changing a device that is interoperable. Is that device interoperable at the cybersecurity level? In a heterogeneous system, most likely not. So there's that interesting layer of the other layer that has been discussed a lot. If I want to integrate the data, for those of you that are familiar with the standards in substations and standards at the control center, the semantics are driven by what is called 61850 SCL Part 6 of 61850, which is the description of the substation control language. That's where I define my elements of the substation measurement system. The control center is driven by SIM 61970, which is Common Information Model, that does not match the SCL description. So if I want to merge the data from SCADA and from substations in this environment, I'm having difficulty because the semantics between my models, data models, are not the same. Now, IEC, the International Electrotechnical Commission, has been sitting on this problem for probably over 10 years now. And supposedly is going to move on that and get it all resolved. But you may have some issues as you look at the implementation that are really putting some of these concepts of data integration and so on at jeopardy unless you have the standards that can regulate that. Finally, I love this example. This is my last example, and that is PMUs. So what you see here is clocks, PMUs, PDCs, the phasor data concentrators, and super PDCs, and so on. Those of you that are familiar with these systems, those are the components of the system. What I'm going to show to you now are two things. One is the standards that exist, and the other one is compliance with standards. Remember, this leads back together to interoperability. That means whether I can grow these systems and how. So standards, I'm not even commenting them, I'm just going to click on them. More than you can chew in one day. You can't read them in one day. You can't read them in 2 days either. You can't read them in 7 days. I can assure you of that because I was the author of some of these, initial author of some of these, and I made them so that you cannot read them in one day. So in any case, how do we make sure that everything meets these standards? So if I take only a portion of this problem, take only PMUs and clocks, nothing else, and I take the standards that correspond to that, which is 118.1, as it happens to be, and I do some tests. On the right-hand side is a test against dynamic requirements in 118.1. And the PMUs, ABCD, and whatnot are different products on the US market. They fall into different categories. On the right-hand side, I have the requirements from the standard. I have S's and F's. S's, well, you know this from school, right? When you get an S on a course that doesn't have grading, it's a satisfactory, at least at A&M, that's what it is. And if you get an F, you don't like it, right? I hope nobody here gets an F. Well, these PMUs got Fs. Not a single one, not a single product on a US market has passed the standard. All of the requirements of the standard. Not a single one. This is an interesting reflection on applications. We are all writing these equations, we love them, and we say this is going to do this and that. Are we really studying the impact of bad data, accuracy of data? If we are not, I can tell you we are off. A little bit off, I guess, but we are off from what we should really be analyzing, right? The same with the clocks, or PDCs, I guess, in this case. I took different PDCs, different PMUs. They didn't match. And I think I took clocks in one other slide, and they didn't match. So anyway, long story short, we have some websites and stuff like that. You can always Google my name and get to these websites. So we are now ready to entertain any questions. I'm sorry I went a little bit over, perhaps a few minutes or whatever I did, but I do apologize for that.
Right, thank you, Mladen. I think we have time for one question. One question.
Maybe we can have time to.
Good.
Only one question, right?
Yes.
Wow. All right. So, Mladen, thank you very much. It's really a very nice presentation. Really appreciate your help. If we assume that the PMU and the Synchro phaser are in the perfect condition, what would be the status of state estimation and load flow? Are these going to be old technologies?
Well, you see, yeah, we need to repeat the question. So the question was, if the PMUs were ideal, if they were measuring everything correctly, would some of these techniques that we use, like load flow simulation and the state estimation, would they become obsolete? The answer is yes and no. And the reason why it's a yes and no is yes, in a sense of what you are measuring. Those are the states, and you can get them. You don't need state estimators. But no, because of the status of everything that we have. First of all, we're not going to get rid of the state estimators easily. They are already part of our system. And secondly, if the PMUs are really not measuring the way we think they are, now, I know your premise was that they are, but they are not. In reality, they are not. Maybe I need a state estimator still to get these measurements reconciled. So the state estimation as a concept has always been there for us to take care of some sort of uncertainty in the measurements, assuming that we are dealing with the good models. So I would say a good approach to eliminating some of those things is over the years to go into better models based on measurements, and then try to see whether I can really get measurements that can match my models, and eventually get convinced that I can get rid of these computational methods. So in some sort of an asymptote that goes beyond my life cycle, we probably will be getting rid of it. It was interesting, just the last point, that Ali Abur, a good friend of many of us here and my neighbor for years, as it happens to be in College Station, has actually studied the sensitivity of the state estimator to additional state measurements and came to a conclusion that there are very few improvements after a few measurements are put in. And so that's another part of integration of these measurements into the state estimator. Maybe we can allow one more. Yeah, because I know people are dying to ask.
Okay, one more.
You had some data available presently that is not used operationally, and you proposed integrating it so that it could be operated, so that it could support decisions. What's the duty cycle on that now if it only is gathered when it's triggered? If you were to gather it more constantly, at the same sampling rate that's used for the operational data, is the infrastructure, does it support that, or is it?
Well, the speakers have a privilege of, expressing their opinion as strongly as they can, and the moment they leave, nobody needs to agree with them. But at the moment when they speak, people tend to listen. It's a fallacy. It's something that shouldn't be done, in my judgment, to try to stream the data as the system goes through the dynamic states. We should actually have very smart monitors that tell us when there is a change of significance in the system. So the concept of the streaming PMU data is, to my understanding, something that we shouldn't be doing. So now, going back, if I am not streaming anything, remember, SCADA doesn't stream the scans. It reports by exception. It's a little bit of a primitive way, but it actually reports by exception. So we should not be streaming the high-resolution data. That doesn't mean that we should be collecting the high-resolution data. We should be. And then developing techniques at the source to tell whether there is enough information to be conveyed and what that is. That is the concept very similar to basically data compression. Because what we are really doing with that step is compressing data, because you are not sending something that is not containing information. And so, to answer your question, when you have an event, it doesn't happen necessarily all over the place. When the relays trip, for example, they trip here, trip there. They don't trip simultaneously on 2,000 places. So that event is a very small amount of data that needs to be transferred. I have implemented commercial systems that are sending this data to the operational, in the operational mode. It takes at the source a second or two to actually conclude not only that event has occurred, but what has occurred. And that is directly sent up. So you have this reporting by exception when the event has occurred, and this preprocessing that takes care of this huge amount of sample data, and yet the information is contained and preserved. So that's the approach that we should be taking.
Good. Well, thank you very much. I think this concludes the formal presentation. If some of you have more questions, I'm sure that Mladen will be happy to answer them individually.
Thank you very much for your attention.